Okay. Given a function f of x, y, 25 minus x squared plus y squared, we usually calculate the partial derivatives with respect to x and y. And then at the point 2, 3, we find that the value of f is 30. So we're looking at the behavior in the neighborhood of the point 2, 3, 30. And here's pretty much all we need to analyze that behavior. So, at 2, 3, 30, partial of f with respect to x, well, it's negative 2x. X is 2, right? What's this mean? This means if you hold y constant, you slice this surface, and of course you know that negative x squared plus y squared is the equation of a hyperbola. This is a hyperboloid. If you slice this hyperboloid, whatever it looks like, for a constant value of y, you get a curve. At this point, the slope of that curve is negative 4. When x is 2, the slope is negative 4. So the y equals 3 slice of the graph looks like what? Well, 25 minus x squared you got z here, you got y here. You have a y-intercept of, sorry, this is x. You have an x-intercept of 5 or negative 5. And when x equals 2, you have a tangent line with a slope of negative 4. Now, when you're calculating partial derivatives and looking at the behavior of a function in the neighborhood, these kinds of sketches can be very useful. You can attempt to sketch the whole three-dimensional function, or you can sketch contours, lines, or whatever, but you want to get a picture of what it is you're dealing with. And this is just a quadratic surface here, okay? Then the y equals 3 slice of the graph looks like this with a slope of negative 4. And the x equals 2 slice, well, it's 25 plus y squared. Of course, here is z equals 25, right? So this is, so this is the point 2, 3, 30 in this slice. Now you got to think through what the slice looks like. We've done a fair amount of that, so you want to maybe look back at your notes or videos or whatever and get the picture. And the x equals 2 slice, again, if x equals 2, well, that's 4 there, and 25 minus 4 is 21 plus y squared. So you have the point 0, 21 here, plus y squared. And when x equals 2, of course, so when y equals 3, then, write it out. Z is 21 plus y squared, when y is 3, your coordinate here is 30. So here's the point 3, 30 on this slice. Up here, I haven't left myself much room to do it, but this would be 230 on the XZ slice. Now this is, again, you're slicing this with a plane parallel to the XZ axis. Here you're slicing this with a plane parallel to the YZ axis. Both of these slices go through this point because we're trying to see what's going on in the neighborhood of this point. So here, what's the slope? The slope is 6. If you take the derivative of this, you get 2y, right? And of course, the derivative is just this. And if y equals 3, which it is on this slice, you're going to get 6 at this point when y is 3. Okay? Similarly, here, the derivative of this function, the y equals 3 slice, is z equals 25, z equals 34 minus x squared. X equals 2 slice is this. And the derivative of this is just negative 2x. We'll have your partial derivative with respect to x. And that gives you the slope of negative 4. Then you put that together into a picture where these things intersect. Okay, these two planes intersect. The picture here is your x picture. Picture here is your y picture. Okay? I think I did it wrong. In the XZ plane, yeah, here, and here, in the YZ, parallel to the YZ plane, it's like this. You're not at the low point. The low point occurs at this point and this point. That would correspond to a saddle point, where the thing drops off like this in the x direction, goes up like this in the y direction. Okay, well, there we have it. So, now we're trying to develop a picture. If I sketch the XZ picture again, and I have this point, and I've already covered up all my chalk, extending this board out. Look at this. You got the tangent vector, which is I don't know what I wanted to write K first. No reason it couldn't be done, it's got a coefficient. There's your I vector minus 4K here. In the YZ plane, and of course implicitly this is 0.2330. In the YZ plane, you've got the point 330 and the vector is j plus 6k in 3 dimensions. These vectors are both tangent to the surface. So these vectors are both tangent to the surface. Z equals f of xy. So I minus 4k cross j plus 6k, which is easy to calculate. You can do the determinant if you like, but I cross j is k. I cross k, you know, do it carefully. I cross k is negative j, right? So I cross 6k is negative 6j. And then negative 4k cross j. Okay? K cross j is negative I. You got a negative on the 4. There it is. Is normal. Okay. Now the equation of the tangent plane. I'm going to have some, oh, I've got some more words for here. So the tangent plane is through the point 2, 3, 30. And normal to what? Put them in IJK order. Normal to this vector. So x, y, z is on the tangent plane if the vector between this and this is perpendicular to this. This is the vector that connects this point and this point. This is a vector in the plane. If and only if perpendicular to this. So this perpendicular to this two vectors are perpendicular if and only if their dot product is 0. So that you have 4x minus 6y plus z equals, that's going to be negative 8, that's going to be positive 18, so that gives you a positive 10. And then minus 30 is minus 20, so you add those up, and I believe you get 20. Okay? there's the equation of the plane, not some formula that you have in front of you when you do your homework, but a process with a picture that uses simple reasoning at every step, simple geometric reasoning, and is much more valuable to most people than a bunch of memorized symbols. Memorized symbols will get you answers, but they won't necessarily give you insight. Now they can, but it's rare that somebody has better symbolic understanding. I'm talking about deep symbolic understanding than geometric understanding. So I kind of recommend this way of doing it. Okay, well, if you want, the equation of the plane is this. Okay? Now at 2, 3, z equals 20 minus 8 plus 18 equals 30. So as a check, the 0.23, bad looking 3, let's see if I can make it worse. Yeah, it's still a bad 3, but maybe it's more recognizable anyway. Okay, 2, 3, 30 is on this plane, as it must be because it's supposed to be a tangent plane at the point 2, 3, 30. So now we have a plane that approximates this surface in the vicinity of 2, 3, 30. Well, yeah. So this approximates xy, f of xy, if xy is near 2, 3. At 2.06, 3.08, the tangent plane approximation is z equals 25 minus 4 times 2.06 plus 3 times plus 6 times 3.08. Now to calculate this, I'm going to say that's 25 minus 8 minus 0.24 plus 18 plus 0.48. You see what I did? I just used a distributive law. 2.06 is 2 plus 0.06. So I just distribute the negative 4 through the 2 plus 0.06. And similarly for the 3.08, you're nodding your head, so I think you understand. Either that or COVID's doing strange things to your neurological circuits. Don't think that's it. Whenever you've been through it. So, haven't shown any lasting effects, which is great. Okay, so anyhow, what do we get? Well, 25 minus 8 plus 18 is 30. And then minus 0.24 plus 0.48 30.24. Now, compare the F at 2.08, 2.06, 3.08, which is 30 point, oh, it's going to be 24 and then a couple decimals, right? What are the decimals? Well, let me just look because I don't want you to identify yourselves, because this video is just so great that we can't afford to have to trash it. 280. Okay? Now let's point out a couple of things. There's your partial f with respect to x, there's your partial f with respect to y, right? So we could also write out change in f is approximately fx delta x plus fy delta y. This is a differential. And I'll say now you ought to go back to your text, Calculus 1 text or any Calculus 1 text, and look up the differential. You really need to understand differential. You did it, but chances are you didn't retain it because you don't see it in a broad enough perspective. Well, here it is in a broader perspective. General expression for the differential of a function of many variables. It doesn't matter how many variables. If you got z, w, k, q, p, then you have fz, delta z. Of course, now it's not going to be a function of two variables. You're going to be graphing it in many dimensions. Okay, and you can't take three-dimensional slices, put them together, kind of like we do the two-dimensional slices here. Put them together to get the tangent line. Okay, but anyhow, that's, and what I just said is really worth thinking about, but you probably don't have time. Okay. Let it make a little impression in your brain. It's not hard, except you can't visualize a graph. So you go to as many variables as you want. It just extends in the obvious way. One dimension it's this, two dimensions it's this, three dimensions be like you'd add an fz delta z and an fw delta w if you got a fourth variable, and so on and so forth. Okay, well now we didn't get everything done that I wanted to because we had some difficulty. I wanted you to work these things out so you'd understand this. I wanted you to get the calculations in your head. Do this calculation, hopefully figure out the tangent plane. Not sure anybody quite got to the tangent plane, but if you understand every aspect of this, you've got a picture. It's going to be very valuable to you in a couple of weeks when you have a midterm exam. Helps bring everything together. Okay? So we'll go on with this, but I really want you to try to digest this as you do in the next assignment. I even forget what the next assignment is now. But we're leading toward the tangent plane. I think that's it. Maybe it's a directional derivative. Okay? Actually, I think we've already done the tangent plane. But, and the directional derivative comes out of this. That's what I'd really hoped to get to. That's the last question in your quiz. So you might want to think about that. Okay? On at least one paper, and I didn't look closely enough at the other to see, I saw the slope in the XY plane of the segment from 2.3 to 2.06, 3.08. Okay? That's a good picture, and that's relevant. Make sure you understand that in 3 dimensions. You're moving in the direction of that slope down in the XY plane. What happens up here? And how's it related to these? Well, it's pretty obvious, but we're going to see how it relates to the angle of that line. And you're probably going to read it. Okay, very good.